Welcome back to a new chapter which has the title Properties of Endomorphisms. It's still part of linear algebra, and before I go on to explain you what we're going to do in this chapter, let me explain you the headline, namely the term endomorphism, which we haven't used yet. Just a side note, this time I'm not doing the mistake of the last chapter, and I assume from the beginning that in the whole chapter 9, K will always be a field, so I don't have to write this down every single time, so K will be some fixed field of numbers. Now, endomorphisms. Definition 9.1. Let V be a vector space over K. An endomorphism of V is something we've seen already quite a few times, namely just a linear map from V to itself. So a homomorphism, this is what we call linear maps alternatively, for which domain and codomain are just the same space. That's everything. So this is just an endomorphism. So we just have one vector space and stay within this space. Now one more term, a bijective linear map going from V to V. So a bijective linear map is what we call an isomorphism. Now in this special case that we have an endomorphism, so that domain and codomain are the same, this is called an automorphism. Okay, so just an automorphism is the same as an endomorphism, which is an isomorphism. Okay. This will probably be the last morphism type that we introduce. So there are more terms in math and in algebra, but this is all we need. So yeah, endomorphism and automorphism, so something we've already seen, but we'll just get some special terms. So by the headline of this chapter, we are going to investigate endomorphisms. So we are going to focus on linear maps which go from one vector space into the same space. There are several phenomena for these maps which cannot be studied for general linear maps, or which make no sense for the general linear maps. And the two main constructions we're going to need are determinants, with which we're going to start immediately. And I will going to explain you later what determinants are. So yeah, in the following, then afterwards, after we've seen determinants, we're going to study eigenvalues of linear maps, which are just particular values that tell us a lot about F, and that gives us a possibility that you have for endomorphisms to give a nice classification of them in some sense. So we can kind of study endomorphisms in greater detail and see and understand them, what they are doing and so on. And yeah, this is what we shall see later. So the first sections of this chapter will be about determinants. And a determinant is something which you can associate later onto an endomorphism, but first we will basically construct this in 3 steps. First, as a general construction of a map which takes vectors and gives out a number. Then we will do determinants of matrices, and then we will go on to endomorphisms. But in general, like if you take the intermediate step of a matrix, this is basically if you have a whole matrix of numbers. A determinant is something which associates to a matrix some certain number, so it's a map from the space of matrices, a set of matrices into the ground field K, some number which already characterizes the matrix in some sense. So we can already read some kind of information from a given matrix just by studying a particular number, for which there are various computation techniques. So this is something you can really compute then, and to really study properties of matrices, as we shall see soon. But first I will introduce the matrix by something which has as input several vectors and gives out a number, and which has certain properties, and yeah, then we will see how the determinant generalizes and what is its meaning later on. So for this next section, which I just call 9.1, definition and construction of the determinant, So for this, we will stay as basic as possible and first give a vague idea of how to construct this and then move our way, as I said, in several steps until we reach the general construction. So in case you're wondering, so if we associate determinants to endomorphism, this is something which is indeed useful. And for example, in the calculus part later on, when we study about high-dimensional derivatives and so on, these determinants can also help us in making several assumptions on calculus and on some geometry of solution sets. In some senses we shall see, but this is towards the end of the semester. But anyway, so this is something that's really useful, although it looks maybe a bit weird in the beginning. So how do we start? We start right off by defining the determinant, and now I'm doing something unusual. I'm not defining this explicitly as a map, but I say that n in n, the determinant is a map which we call det, det, which takes vectors from k to the n and n many. This would be in this strange notation kn to the n, so as a Cartesian product, by which I mean k to the n times k to the n times and so on, times k to the n, so the n-fold Cartesian product. So we just take n different vectors from k to the n and have those as inputs of the map det. And as a result, we get just back a number, an element of k. Okay, but instead of writing down explicit formula for the determinants, this is something we will do later, I want to characterize this by saying this is a map which has certain properties. And now I'm saying the determinant because it will turn out later that this map is really unique if we want this to have the properties that I will now sketch. And as a separate that so far the determinant only makes sense if we have some uniqueness, which we shall see later on. But I want just basically a wish list of properties. So I want to have 3 different properties, and my wish is that it satisfies these properties. And afterwards we will see there is indeed such a map which has these properties and which gives which really does the job. But since the explicit definition is not really intuitive, it's a long, quite complicated formula, it's more helpful to see it this way as a map which has some useful properties. Okay, the first of them, the determinant det is multilinear. This I will define in a more general range later on. So for now, I'm just going to explicitly say what this means. Namely, for each I, or for all I from 1 to n, then I take n different vectors v1 to vn, and I take one additional vector wi. These are elements of k to the n. And I want to take 2 numbers, lambda and mu in k. And what do I demand? I want that if I take the determinant of v1 to vi minus 1, I just take these vectors, and in the ith component I have lambda times vi plus mu times wi, and the remaining vectors are just vi plus 1 and so on to vn. This is supposed to be, and now the idea is that it should behave linear in this ith coordinate. So if we forget about all the other vectors here, about these, if we have some map which would only have this as input, a linear map then would give us lambda times f of vi plus mu times f of wi. This is kind of linearity what it does. In here I want to demand is that if I keep these vectors fixed, v1 to vi minus 1 and vi plus 1 to vn, then it should behave, it should be a linear map in this ith component. And by this I mean this here is supposed to be lambda times the determinant of v1 to vi minus 1 and now just vi in this ith component, vn, and now the second part of the second aspect of linearity plus, this is also what linearity does, mu times the determinant of v1 to vi minus 1 wi, vi plus 1 to vn. This is supposed to hold true for all choices of vectors and for all I. So this means like in each component of these n component, it should be linear, so to say. Okay, this is the first thing I want to have. The next thing might look a bit more mysterious. The determinant is supposed to be alternating. I might get to a more general definition of this term later on. I just want to drop the word at this moment, so it's not really important. It's just what I'm now doing is really what's interesting. So if we have n different vectors, so which we insert into the determinant. If we have two vectors among these Vn to Vn which are the same. So if there are I and j between 1 and n, such that I is not equal to j, then it's obvious, with I not equal to j, but such that Vi coincides with Vj. So if two of the inputs are the same, then I want that the determinant of V1 to Vn is always 0. So as soon as two coincide, boom, 0. Okay, so this is something not that intuitive at this moment, but this is what I demand. And the third property from my wish list is that the determinant is supposed to be normed in a certain sense. Also, this is a term which we will maybe see a bit more general later on, so this is not important, but I just want a similar thing. Simple thing. If I include the canonical basis E1, E2 to En, so the standard vectors 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on until 0, 0, 0, 0, 1, the last vector. This is supposed to be 1. So where E1 to En is the canonical basis of k to the n. Okay, so this is my wish list. These three properties I want my map to satisfy. And although we will shall later on see the explicit form, it turns out that for many purposes, it's just mostly important to know that the determinant has these three properties. This is basically all you need for many proofs and without taking explicit formulas or something. Although we will have some computational methods later and computational results where we need the explicit formula, but these are the most important properties. So this is what we wish. Now, we assume for the moment, just for a little bit, that we have such a map which has these properties. Then we can derive that it has another interesting property, namely Theorem 9.3. So that n in n, ij between 1 and n, and just assume that I is smaller than or equal to j. Then, for all choices of vectors v1 to vn in k to the n, we get the following. The determinant of v1, and now let me expand this expression here a bit. I want to write down, so we just have v1 to vn, but let me emphasize here the ith and the jth vector. So vi minus 1, vi plus 1, and so on. Then vj minus 1, vj plus 1 to vn. Now, what happens if I swap this one and this one? So I just exchange them, which means then I would take the determinant of v1 to vi minus 1, vj, and vi plus 1, and here vj minus 1, vi, vj plus 1 to vn. I claim that we can already derive from these properties that then this here is minus this here. So if we swap two elements, we just get a sign change, but otherwise nothing happens. This already follows from the previous properties. Actually, we only need the properties 1 and 2. This norm property is not important for this. And let me show you. Namely, so by the defining properties of the determinant, by which I mean these three properties, we get the following. If we now choose a slightly different set of input vectors, if we take that of v1 to vi minus 1, and now in the ith component we put in vi plus vj, and in the jth component We also put in Vi plus Vj. So we now know, since it's alternating, so by this property here we have two vectors which are obviously identical. So by property 2, this must be 0. Now, we can now use the linearity properties, because here's a sum. So by property 1, so by this multilinearity property, this is compatible with sums. I mean, here you just have to think of lambda and mu to be equal to 1. And then we already have these properties. Now we just have to pay attention because we have two sums here. And we're going to expand this in two steps. Namely, we first, so keep in mind, to apply this multilinearity, we just need to have one component as variable and the other ones as fixed. So let's keep this fixed for the moment. Then multilinearity says, so this is property 1, that this is the same as the determinant of V1 to Vi minus 1, and now just Vi plus 1, and so on to Vj minus 1. And here we leave everything as it is. Vi plus Vj. So it's slightly different computation than with with linear maps. So just here, so if we would have some linear addition in k to the n or something. So here we keep this as fixed and expand the first one. And now, yeah, okay, this is the first summand that we get from here, plus the determinant of V1 to Vi minus 1, Vj, Vi plus 1, and so on, Vj minus 1, here everything is as it is, Vi plus Vj, Vj plus 1, Vn. Okay. Now in both of these summands we can do the same trick with this component here. So keep everything fixed and expand the summands. And this we need to do separately. So this time we get 4 summands. First of all, from this one we get that V1 to Vi minus 1, comma Vi plus 1, Vj minus 1, Vj plus 1, to Vn, plus determinant of V1, Vi minus 1, Vi plus 1, Vj minus 1, Vj plus 1, Vn. Okay, this was expanding this one, and now the same with this term here. So it's just the same summons, except that we get a j instead of an I here in front. So we get the determinant of V1 to Vi minus 1, Vj, Vi plus 1, Vj minus 1, Vi, Vj plus 1. Okay, and finally, the determinant of V1, Vi minus 1, Vj, Vi plus 1, and Vj minus 1, Vj, Vj plus 1, Vn. So, that was work. Let me get some colored chalk. Because now we're almost done. So basically, if we take now a look at this, so here we have 2 times the same input. We have twice Vi in separate positions, so just by the alternating property, so here we need, when I do this with 1 and 2, so by this alternating property, the first summand is 0. Okay, and the same goes for the final summand. The determinant, here we have Vj, here we have Vj, so by the alternating property, this must go as well. So this means the sum of these two is 0, and if we bring just this one to the other side, this means this summand is minus this summand. And if we take a look at the claim, that's precisely what I wanted to show. That's this here. So not writing this down explicitly again, but this is minus this, and so we get the claim. And so we're done. Okay. This was more work to write than to really think. So this is really just some standard computation. And so this is already some property. There are more properties that can already be derived from this wish list of properties. So from these 3 that we had. But I will not do more of them. But instead now I want to go on and check if such map really exists and what can we say about this map and how can we really construct this as numbers to get this map, to get these properties and how we get uniqueness. Let me erase and then we'll do that. To give an explicit definition of a determinant, we need a little bit of group theory, so a little knowledge about so-called permutation groups. So if this was a proper 2-semester linear algebra course for mathematicians, you would do a lot of group theory and a lot about groups and so on. But since this is only, not only, but this is a course aimed at physicists, and this is really something which is just not relevant for you, this group theory, all that much. I will just give a very brief summary of the important things and give you one result about permutation groups, which should be interesting. Also, yeah, a few little results, which we shall need later on, but I will not prove them. So this is something that is you can read up in linear algebra books, in many books there should be proofs included, but for you this is really not that relevant, so let me just keep it very brief. Okay, definition. 9.4. Okay, we take some n in n as fixed, and now we start very elementary. The permutation group of degree n, and yes, group in the sense of mathematics 1, where we learned what a group is Sn, and as a set, this is defined to be the set of all maps from the set 1 to n, so a set with n elements on to 1 to n, such that sigma is bijective. Okay, so we take n different elements and map them bijectively on this, and basically this means we reorder these elements. For example, if we had a stack of cards, a deck of cards which has n different playing cards, and we would just shuffle these cards and look at the result would be a permutation. This is just a reordering, so a reordering of the whole deck, so a shuffle, so to say, of these elements. This is what we study here, so all ways of kind of reorganizing n elements in a different way. Now, this is a space of maps from this set to this set, which is bijective, and Sn, together with the composition of maps, this is of course something that's defined on there, and we know that composition is again a map from this space to this space, since it's all the same, and the composition of bijective maps is bijective. So this, together with the composition, is a group. And this is something we've already seen, actually, because this is a special case, if you have a very good memory. This was I've written down the precise date. Yeah, this was in Mathematics 1, sheet 0. So the very first sheet, when you were probably totally shocked at what you all have to endure in mathematics. And there it was exercise 2. There we saw kind of that the set of bijections of an arbitrary set together with the composition is a group. So this is really indeed a special case here. Okay, this is the permutation group, so the set of all reorderings of n elements. Now, the elements of this group, so each Sn, so each such map is called a permutation. Okay, and we finally want to give a particular name to a special kind of permutation. Start right here. So if we take some tau in Sn, this is called a transposition. By the way, this might be the first time I'm using delta tau. I don't know, but I think sigma I had already, so I might get the whole Greek alphabet until the end of the semester. We'll see. So it's called a transposition if it's a special type of permutation, namely it just swaps 2 elements and leaves the rest as it is. Meaning if there are 2 elements, I and j, so in this set from 1 to n, such that tau of I is j, tau of j is I, so those 2 switch places, and the rest stays as it is. tau of k is k for all k in the set without I and j. Okay, so transposition is a special kind of reordering, a very simple reordering which just swaps two things and not more than that. Okay, now in this following theorem I want to summarize some facts from group theory, and I will not prove them as I already said, but these are kind of things which are not that hard to see actually, and this is not, let me state the results. So for each n in N, the group Sn has, so the question is how many permutations are there? And the answer is the number of elements of this group is n factorial. This is how these factorials often turn up because of some combinatorics, that's what we call it actually. So kind of this is, if you study this, so there's a systematic way of proving this. I will not do this here. Basically, the whole number will not be relevant for what's to come next, but important is there are finitely many. So this is really a finite group. So it's the underlying set here, this Sn, this is a finite set. This is important. Okay, and part B, every permutation is given as the composition of finitely many transpositions. Transpositions. Okay, when I learned this theorem first in linear algebra, I still remember because in the lecture notes my professor had just written, so there was this theorem, every permutation is given as a composition of many transpositions. Proof, every 5-year-old kid knows this. Because this is something easy to see, like if you want to permute something, assume you have n elements which are in a particular order, so I don't know, some cards or like, I don't know, pots or whatever, so you want to reorder something. How can you reorder this? You just switch 2, swap 2, swap 2, swap 2, and so on and so on and so on. This is basically what you do in gambling, kind of, when you kind of, I don't know what's it called in English, but when you have 3 different cups and there is a board on the one cup and someone is just shuffling these cups, he's just switching and switching and switching and switching and so on, and so you get confused and don't find the right cup. Anyway, but this is the idea. So you can achieve every reordering by just swapping 2 elements, swapping another 2, swapping another 2, swapping and swapping and swapping and so on. If you don't believe this, just put n objects in front of you and try to get to a different ordering of these objects just by swapping, and you will find out this works. So this is what I will not prove. Okay, now, why is this interesting? This is interesting because this second part gives rise to some construction that will be needed for the determinant, and we shall see later on why. Definition 9.6. So let sigma, first let n in n, and let sigma be a permutation of degree n, so sigma in Sn. If we have this as, so we now know this is a composition of finitely many transpositions. So if we have transpositions tau 1 to tau k, are transpositions, so for some number k, such that sigma is then really given as tau 1 composed with tau 2 and so on, then we construct the following. We call the following number sine of sigma. This is defined then to be -1 to the k. So the number of transpositions that we needed to achieve this permutation here, this is called the sine of sigma. So the sine of a permutation. Okay, this is something you can write down. However, there's one small problem. This way of writing some permutation as a composition of transpositions, many complicated words in here. So writing this permutation is a composition of transpositions, of k many. This representation here as such a composition is not unique. For example, if you have some particular ordering and just swap two objects and swap the same objects again, you have added two transpositions, but the result is the same. So you can always find many, many ways of writing a permutation as a composition of transpositions. Let's just fix this as a remark. Okay, so representing sigma as a composition of transpositions is not unique. However, if we have two different ways of writing this, so for example, if tau 1 to tau k, and now another Greek letter, rho 1 to rho L for some other number, in Sn are transpositions with sigma is the composition tau 1 composed with tau 2 and so on composed with tau k, but it's also the composition rho 1 composed with rho 2 and so on with rho L. So if we have these two different ways, then of course k and L might be different numbers, so we have no guarantee that this is well defined. So on the one hand, this would be minus 1 to the k would be the sign. This would then ensure that minus 1 to the L would be the sign. But it turns out, and this is something that I will not prove, either both numbers are even or both numbers are odd. Both k and L are even or both are odd. And this means, so if here for the sign, the only interesting thing for this, or the only relevant thing is if k is an even number or an odd number. If it's an even number, this is plus 1. If it's an odd number, it's minus 1. So everything else doesn't matter. So this means, while this k is not unique, this there is well defined because it doesn't depend on this particular k because they always give the same sign if we have the same permutation. So this means the sign of sigma is well defined. And again, I'm not proving this observation because it's not too important for you. Secondly, as part 2 of this remark, by definition of the signs, or by definition of the sign of sigma, if we take two permutations, sigma 1 and sigma 2 in Sn, we get the following. So the sign of the composition of these two, composition of a permutation, of permutations is a permutation. Now, what is the sign of the composition? We know that if we have, like, if we need k many steps to get k many transpositions for sigma 1 and L many transpositions to get sigma 2, we just have to do them one after another, all of them. So we need k plus L many compositions to get transpositions to get there, so to get to this. Now, we have if this would have sign minus 1 to the k, this would have minus 1 to the L. The result must then have minus 1 to the k plus L, which is the same as minus 1 to the k times minus 1 to the L. And by this argument, we get that the sign of the composition is the product of the two signs. This sign of a composition is the sign of the product. This is also something I won't do the formal proof. I just sketched how this works. But we shall see we shall use this later on. Now, I'm using now I want to state the explicit version of the determinant, but since I need quite some space for this, let me erase at this point, and then we will see finally the explicit formula for determinant and show it. We will now discuss the existence of a unique function which has the properties of the determinant that I had on my wish list in the definition. So this is a big theorem, Theorem 9.8, and we do the following. Let n and n, as usual, then there exists unique function, unique map that from Kn times Kn. So again, we can take n many factors here. Unique map, which has properties 1, 2, and 3. So 1, 2, 3 from definition 9.2. And we can give the explicit formula if we take A1 to AN. These are now vectors in Kn. And if we give the entries names, so AI is supposed to be AI1, AI2, AIN. So this for all I between 1 and n. Then we have a really explicit formula in terms of these numbers here, which are in the components there. So something you can really compute. Then, and now brace yourselves, the determinant from of A1 to AN is given as a sum, where the sum is indexed over all permutations of n elements. And I said as n has finitely many elements, so this is really a finite sum, so we don't need to worry, it's not a series or anything. So finite sum. And now we get first the sign of the permutation, sign of sigma, times, and now we get an interesting product of entries of these vectors. A1 sigma of 1 times A2 sigma of 2 until AN sigma of n. So the second component, we take, this basically means since we have 1, 2, and so on to n, we take one component from each vector and take the product of them, and we do it such that basically we have that they in order to have the same order here in the entry here. So we take this sum of all these possible combinations of taking a product here. Okay, this looks really mysterious, I must admit, if you see this for the first time. Okay, let me show you that this exists and has this property, so that this really is a determinant. So first of all, assume we have a determinant function. So assume some function, which is not necessarily defined like this, but just some function that from Kn to the power of n to k has properties 1, 2, and 3. Now I want to show that it necessarily satisfies this formula. How do I do this? So we can write every vector in an unnecessarily complicated way, namely this here is basically these entries here. If you recall, the entries of such a vector are the coefficients if I write this as a linear combination in terms of the canonical basis. So just explicitly, this is maybe even easier to write down than to formulate. This is the sum of all j in from 1 to n, aij times ej. So the jth canonical basis vector. Now this is just, obvious. Or not very obvious, but this is kind of this is very simple. This is nothing fancy that's standing there. So since this holds for all I, we compute the following. So if we take that, so a function satisfying these properties of A1 to AN, so let's now write the first of these vectors in this form. Then we get, sorry, I already made the first mistake since it's a horrible computation. Now let's write A1 as this in the form of this sum, and now this time I want to sum, don't call it j the index here, but j1, since there are more j's to come, so to say. j1 goes from 1 to n, and now here we have A1 j ej. So the rest is then A2 to AN. This stays as it is. Now we can already use the first determinant property, because now we can use multilinearity. This is a finite sum, and so this linearity principle, I've only formulated this for the linear combination of two elements, and as we've seen already before, this already then goes down to finitely many. So this, you can really do the same computation here, namely this is, so by the property 1, so multilinearity, This is the same as the sum from J1 equals 1 to n of A1 J1 times the determinant of EJ1 A2 to AN. Okay, so here is now an EG1, and this is of course now a sum of finitely many numbers. Now we can do the same thing for A2. This is the same as the sum J1 equals 1 to n A1 J1. And now let's expand the second component here. This is the sum, and now I call the index J2. J2 goes from 1 to n, A2 J2 times EJ2, and the rest is then A3 to AN. And now by multilinearity again, we can do the same thing. This is now the same by property 1 as the sum J1 equals 1 to n. And now here inside the sum we have another sum, and I can leave out the parentheses because it's finitely many, so the ordering doesn't matter. The sum J2 equals 1 to n. So basically, so here would be inside the sum, but there are finitely many. You realize once I've written down the term, A1 J1, and now we've got A2 J2 as coefficients, and now we have the determinant of EJ1 EJ2, and now A3 to AN. And now guess what? We can do the same thing for A3 and so on and so on and so on until we arrive at the end. So until we really have done this for every term. So we can do this again and again. Let me just abbreviate this by dot, dot, dot. But since this is finitely many steps, this doesn't need an induction proof or something. So in the end, when we have reached that, what will the result look like? The result will be the following, and this now looks really messy. So we would have the sum from J1 equals 1 to n, sum from J2 equals 1 to n, and J3, and so on until Jn. So we would have n many sums. And there's a more economic way of writing this. This is the sum from k equals 1 to n, and now we take the sum over jk equals 1 to n. And here I've used, if you think about this, the details are not that important. They can reorder finitely many terms always. And then we would have A1 J1, A2 J2, and so on until AN Jn. And finally, the determinant of EJ1, EJ2 to EJN. Okay. Now, this looks weird, but we're getting closer to what we want to. So here we have a product of all these elements. And here we have this. And now all of these j's, they can be anything between 1 and n. Now, we have to use the different properties of a determinant at this point. Now, we can see if two of these indices, two of these, j1 to jn, if two of them are the same, then we know that we have twice the same vector in here. But then we know it's, because of this alternating property, the determinant vanishes. So since det ej1 to ejn is equal to 0 if there are kl in 1 to n with k not equal to l, but jk is equal to jl. We know that the summands that belong to these possibilities are all vanishing. So we can disregard in this huge sum everything for which two of these j's are the same element. Okay, now this means the summand, the corresponding summands, to be precise, if you consider one of these summands as fixed, the corresponding summand is non-vanishing if and only if the set of all these indices, which means they're all different. So this means these are n different numbers out of 1 to n. This means every number needs to appear once here. So this means the set of indices, if we just consider this as a set without any ordering, j1 to jn, this must be 1, 2 to n. So each of them must appear there. And this is the case if and only if, and now we're coming to the permutations, if and only if the map sigma, which goes from 1 to n to 1 to n, which with sigma of k equals jk, so which associates with every k the corresponding jk, if this is a permutation. This is what a permutation does, it's bijective. So, and also, conversely, to every permutation, sigma, we can associate some combination of indices by just putting j1 to be sigma of 1, j2 to be sigma of 2, and so on. So we can associate a non-vanishing summand. So this means instead of having this index notation here, this here is precisely the same as expressing this via permutations. Namely, we get that, okay, we started with that of a1 to an, if you already forgot. It was a straight line computation. This is now the same as the sum over all sigma in Sn. And now we have a1 sigma of 1, a2 sigma of 2, and so on to an sigma of n. And now this determinant part becomes that of e sigma of 1, oops, e sigma of 2, and e sigma of n, and so it becomes that. So this is just some reordering of these, of the canonical basis. Since every number here appears once, so these vectors here, every vector from the canonical basis appears precisely once in these inputs, and they just might be just messed up. So there might be, the order might be strange. So remains to show, or remains to study the relation between these guys, so that of e sigma 1 to e sigma of n, and with one case that we know, namely we have seen, this was property 3, which we haven't used so far, of the determinant. Yes, so here we had, just mentioned explicitly, here was property 2, so this was the alternating property. Before we used multilinearity, here we used the alternating part, and now we use property 3. Namely, property 3 was that if we have the standard order, if they're really ordered in the way we want it, then we get 1. So the question is, if the order is messed up, what happens? And here it turns out that this theorem, that's not important, that theorem after the definition, if I swap two elements, the sign of the determinant changes. And of course, this is some permutation of these two, so we kind of need to bring them into the right position. And we have seen every permutation is given as a composition of transpositions, and the transposition here will just mean swapping two elements. So a transposition will change the sign. Namely, just to do this once explicitly, so that sigma in Sn, and that tau and sigma prime also be in Sn with tau transposition. Such that sigma is tau composed with sigma prime. So we have seen sigma is a composition of transpositions, so we can always find one transposition and then some rest, and we could further decompose this into transposition. But just for what I want to show now, we have these these transpositions. Then the determinant of e sigma of 1 to e sigma of n. Now this would be, just by construction here, the determinant of e of tau of sigma prime of 1 until e of tau of sigma prime of n. Now the effect of putting tau on is just, since it's the transposition, swapping two elements. And we've seen that, so if we forget about this tau, now if we do not swap this element, or have the different order here, then this changes the sign by 1. So this is, or by -1. So this becomes minus by theorem, which was 9.3. 9.3, this is minus the determinant of E sigma prime of 1, E sigma prime of n. Okay, so from this form here, we can now do this thing over and over and write this as a composition of k many transpositions. So that if we have sigma itself given as the composition of k many transpositions, we can just do this k many times and always get a sign change. So the actual sign in the end would be minus 1 to the k, and this was by definition the sign of the permutation. So it follows that the determinant of E sigma of 1 to E sigma of n is simply the sign of the permutation times the determinant of E1 to En, and there we've already seen just by assumption, so that was assumption 3, this is just 1, and so this is just sine of sigma. Okay, now we've seen if we have such a determinant function, so if we now insert sine of sigma in here, we get the formula we claimed. This is precisely what stands there. So we've seen if we have a determinant which has, just by definition, these three properties, it must be of this form. So this is unique. So if there is a determinant, it must be this. But what we still need to show is that this is indeed a determinant, namely that if we define that by this expression here, that it satisfies the three properties of a determinant. And this is what we will do after erasing. So this is the expression for the determinant that we have derived, and we need to show that this is indeed a determinant by showing the three properties. So starting with property 1, the multilinearity. Now, if we take I, so a1 to an I consider now as fixed, that I be between 1 and n, and that bi with components bi1 to bin be another vector in Kn, and that lambda and mu be elements of the field K. Then the determinant of a1 to ai minus 1, and now we need to check that if we put in the ith component, this linear combination, lambda times ai plus mu times bi, and leave the rest as ai plus 1 to an. So what does this mean? This means that here this multiplication is defined component-wise. So if we insert this formula there, so we're somewhere, so the only entry which is now, which is decisive here is ai sigma of I. This is the one that's kind of influenced by this here. But this means that since the entries of these vectors here are lambda aij plus mu bij, which means that in each of these sums we get the following. So this is sum sigma in Sn, sine of sigma a1 sigma of 1, and so on, to a I minus 1 sigma I minus 1. And now the ith entry is lambda ai sigma of I, plus mu b I sigma of I, so the corresponding component here. And the rest stays as it was, a I plus 1 sigma I plus 1, and so on to a n sigma of n. Okay, now we see that in each of these sums belonging to each sigma, we can just, these are just field elements that I want, and now just using the field properties, I can use this in every summand individually. So this means this is the sum as the same as the sum over sigma in Sn, where we now take, sine of sigma, and now we have lambda times a1 sigma of 1, and so on, ai minus 1 sigma of I minus 1, ai sigma of I, and so on. I'm not doing this, all of these elements, a n sigma of n, plus, and now in this, Now the layout is going wrong, okay. Now we further get that the second part would be mu times A1 sigma of 1, 2, and now in the ith component, let me just abbreviate, this would be Bi sigma of I, 2in sigma of n. Okay, so, and since this is a finite sum, we can also use distributivity and just take this sum over this and the sum over them separately and put lambda and mu's in front, meaning we get lambda of the sum sigma in Sn sine sigma, and now we have A1 sigma of 1 A, and so the middle is just AI sigma of I in the ith component to AN sigma of n plus mu times the sum over sigma in Sn, the sine of sigma, A1 sigma of 1, and in the ith component this time Bi sigma of I to AN sigma of n. And if we take a close look at these terms, this is just the determinant of, so lambda times the determinant of A1 to AN. And this is then, if we take another close look, mu times the determinant of, and now simply the term we get by replacing AI by Bi. And this is multilinearity. This is what we wanted. Okay, messy computation, and the bad news is the computation for property 2 is even messier. But the good news is I'm not going to do this here. This is in the lecture notes. This is really tedious, and we can really show that this is alternating, but it's just a long, it's not a long argument that I will skip at this point. Now the interesting part now becomes what happens if it's normed. Is it normed? So what happens if we put in the canonical basis as vectors here? Now, this means if AI is EI for all I, so the ith vector of the canonical basis, then this means Aij, so the jth component of AI. What is the jth component of the ith base vector? This is 0 if we're not in the ith component and 1 if we're in the ith component. This means this is the same by the notation we used previously as delta ij, this Kronecker delta, meaning we have 1 if I is equal to j, and 0 if I is not equal to j. So if we have this, this means that if we take these products that appear here, A1 sigma of 1, A2 sigma of 2, to AN sigma of n. So when is this non-vanishing? The only thing that can happen here, so we always need I to be equal to j, otherwise, so they all need to have this property because otherwise the sum would be vanishing, meaning sigma 1 must be 1, this must be 2, here must be n, and so on. So sigma of I is equal to I for all I in 1 to n, and this map is called the identity. So sigma is equal to the identity. Now, this means this is the only non-vanishing thing here. And if we look at the formula of the determinant, this means that the determinant of E1 to En is the only thing that remains is the sign of sigma, the identity, or other sum. So there's only one sum left, the identity here. And now we get A11, A2, 2, and so on to ANN. So these are all equal to 1. So this doesn't matter. And the sign of the identity, how many transpositions do we need to get the identity? None, for example. Or you could also take 2, you just switch 2 and switch them right back, and they are as we were. So the sign of this is 1 as well, plus 1. So they are all equal to 1, so this is 1. And this is what we needed to have it normed. So the explicit expression defines a determinant. The explicit expression has properties 1, 2, 3. So we've shown that actually such a determinant exists and just constructed it. And now we have the explicit formula for such a determinant. Okay, this was very technical, a lot of small, tedious computations. Now we will take the step 2 in the next section. We'll stop the section here, and then in the next section we will go to matrices and then on to endomorphisms. But the focus will be now on matrices and to determinants of matrices and see what we can do with them. And there we can also see why we are actually studying the determinant and why is it interesting, so to say. See you then.